Hey everyone, today we're talking about the light coming from stars. And maybe during, this unit where we're talking about stars, maybe you've had in the back of your head the question, how do we know so much about stars even though they're so far away? Which is a great question. And the short answer is really just we study the light coming from stars. And today we're going to look at the specific tool we use and what we really see when we look at stars. So in your notes, we're looking at the section on spectroscope. So a spectroscope is just a tool that we use to study light from stars. And it can really show us some important things. So if you're looking at the notes and you're looking at the slideshow now, the things that a spectroscope can tell us about a star is just the elements, okay, the composition, which is really helpful. And we're gonna see examples of that later. It can show us the temperature, okay, based sometimes on color, the state of matter, and stars' movement, which we'll also talk about later. How can we really tell if stars are moving towards or away from Earth? When we look at light coming from a star through a spectroscope, there are three different types of light spectrum that we see. The first type of light is just visible light continuous spectrum. And this is something you're familiar with because you've all seen a rainbow and maybe you've heard the phrase Roy G. Biv. Red, orange, yellow, green, blue, violet. Those colors in that order, that's what we're talking about. That's the rainbow, that's visible light. And each of those colors represents a wavelength of energy, where red represents a very long wavelength of energy. And then blue on the opposite side of that spectrum is a shorter wavelength. And that's going to be really important later on in today's video. The second type of spectrum is bright line spectrum, where from Earth we don't get the entire rainbow, we don't get Roy G. Biv, we only get small pieces that were emitted from a low pressure gas. So when you look at a spectroscope, it would be mainly dark, except there would be these individual wavelengths of light showing up as colored bars. And it's really cool that every single element on the periodic table has a unique set of these bright line spectrum, these colored bars. So when you see just hydrogen, it will always have the same exact wavelengths of light, the same colored bars. And that wavelength for hydrogen is different than the wavelengths that are emitted for helium or carbon or oxygen or any other element. They all have a unique pattern, almost like a fingerprint for a person, a human. The last type of visible light spectrum is dark line spectrum or absorption spectrum. And I think this one's the coolest because you start out seeing the rainbow, but then unlike the bright line spectrum, this is dark line. So you see the rainbow, but now we're subtracting individual wavelengths or individual colors that are part of Roy G. Biv, that are part of the rainbow. So we're removing certain wavelengths, they're being absorbed. So how can we use this information to tell if a star is moving at all? And that brings us to the Doppler effect. And the Doppler effect is produced when an object is moving either towards the energy it's producing or it's moving away from the energy it's producing. And a lot of times we think of the Doppler effect here on Earth with sound, because this is something that we see on a racetrack with cars. And you don't have to think that hard because I think we all know the sound that I'm talking about when a car whips around a racetrack and speeds and past the stands. We all know that kind of revving sound that kind of lingers as it passes. And you're probably doing it out loud or maybe like in your head right now. Vroom. That was really bad, but we all know that sound. And the same type of thing occurs with light. Sound is a wavelength and light is a wavelength. So when light is produced by a star and the star moves into its own light, it actually shortens that wavelength. And same thing if the star is producing light and moving away from the light it's producing, it stretches that wavelength out. And so what does that really look like here on Earth? On Earth, we would see those bright lines from the bright line emission or the absorption spectrum. Either of those spectrums would have the same pattern of bars, only shifted towards the blue side of the spectrum if the star was moving towards us. And if it was moving away from us, it would have that same pattern shifted more towards the red side of the spectrum. So the spacing between the bars, like the number, would be the same. The only thing that'd be different is their location on the continuous spectrum Roy G. Biv. They'd either be pushed towards the blue side if they're moving towards us, or they'd be pushed towards the red side if they're moving away from us. And we have specific names for those. If a star is moving towards us and it looks more blue, we just simply call that a blue shift. And if a star is moving away from us and it looks more red, then we call that a red shift. That's about all we have to talk about for light coming from stars. And again, we know a lot about stars just simply based on the light that comes from the star. If you have any questions, please make sure to ask.